All right, so when we began talking about how wavelengths and pitches of audible sounds can be affected, especially in the context of musical instruments, we started by talking about strings, which I think makes sense because you can visualize a string. You can actually see it vibrating. So you can see the effect of shortening the wavelength, like placing your finger on a guitar string on the fretboard. You can see the effect that has on the wavelength and how it affects the pitch. The same type of thing is happening with wind instruments. We can affect the wavelength, which affects the pitch, but it's harder to visualize. But a similar thing is in fact going on, and we can take a look at that as well. So if we have an open tube, like a flute, let's say, a simple open tube wind instrument, we we want to, in order to get these nice clean notes, we want to have a harmonic frequency. So we can start with the first harmonic, where we have the high point of the wave and the low point of the wave, both at the open end of the length of our tube. So if we create a standing wave like this, then the antinodes at the end are going to vibrate up and down, and we'll have a node right at the middle. This point is going to remain relatively fixed, and then the wave at this end is going to vibrate up and down. So this would create our first harmonic or fundamental frequency. Now if we were to look at the full wavelength, this would have to come all the way back down, and then I'm going to shorten here because I'm going to run out of room, all the way down to the node position, and then down to the bottom here. So what we end up with is a curve that goes up and over, and then down and over, and so the relationship between the wavelength and the length of the tube is similar to the standing wave on a guitar string, that the length of the tube is equal to half of the wavelength. Okay, and if we take that a step further, since the frequency of a note is equal to velocity over wavelength, and the wavelength is equal to 2 times the length of the tube, we can say that's velocity over 2L. So for the first harmonic frequency, we've got the velocity, the frequency equals velocity over 2L. Okay, then if we think about other ways in which we can achieve this antinode at the end of the tube, well, we can start with an antinode, come down, hit a node, come all the way down, and rather than this antinode being at the end of the tube, we're going to work our way back up, hit another node, and come up to the very top. Now we've achieved another antinode at the end of the tube. That's going to produce that nice harmonic tone. And if we look at the comparison between the length of the tube versus the wavelength of our wave, we've started at the top, came down, we came back to the top. So in this particular case, with the second harmonic, the wavelength is equal to the length of the tube. And if we go on to the next one here, starting at an antinode, we would come down, back up, and down again. And so we've got another antinode at the end. How does the wavelength compare to the length of the tube? Well, if we start here, down and back up, this is one full wavelength. And then in addition to that, we have another half of a wavelength. So we've got 1.5 or 3/2 of the wavelength equals the length of the tube. And so the frequency is equal to 3/2 V over L, or 3 times the original frequency. So we have our fundamental frequency, 2 times that frequency, 3 times that frequency, and so on. We can see a pattern here. The next one would be 4 times the frequency. And the wavelength, we start off with half, then 1, or that could also be written as 2/2, then 3/2. The next one would be 4/2, or 2. The next one, if we were to do another one down here, would be 2 times the wavelength equals the length of the tube. And the fourth harmonic frequency would equal 4 times the original fundamental frequency. So we've established a pattern here for open tubes, like flutes and clarinets and things like that. Now, if you've got yourself a jug band and you're blowing across the top of a bottle, you can make that. You can make a sound. You can make a tone with that, and by filling the bottles with varying levels of fluid, we can effectively shorten the length of that closed tube and get higher notes. Now the difference here is we still want to have an antinode at the open end. We want that wave to be fluttering up and down right at the opening. But at the closed end of the tube, we want to have a node rather than an antinode. So in a closed tube, we have our first harmonic frequency at a point where, if we trace this down, it would come down to the node, it would come all the way down to the bottom, and then it would have to come back up and over again. So this is actually just a fourth of the wavelength. This fundamental harmonic is just from the top down. We would then also have to do a second quarter to get to the bottom, third quarter, and then finally the full wavelength here. So we're basically breaking that wavelength up into 4 pieces, and this is just the first fourth of it. So for the harmonic, the fundamental harmonic for a closed tube, the length of the tube is equal a fourth of the wavelength. And the frequency is equal to, I know I've kind of written over it here, but that's equal to the velocity over 4 times L. And then if we continue with this pattern, increasing these harmonic tones, the other way we can start with a node at the closed end and an antinode at the bottom end would be that would be half of a wavelength starting at A, going down to the bottom, and then another quarter back up to the top. So that's 1, 2, 3 quarters. So in this case, the length of the tube is equal to 3 quarters of a wavelength. And then the next one here, the other way we would get it would be to go down, back up. Now that would be a full wavelength right there, starting at the open end and ending there. And then to it, we have to add another quarter of a wavelength. So again, we can see a pattern here developing. It's not the same as the open tube, but it's a similar pattern where we're going from, in this case, a quarter to 3 quarters to 5 quarters. The next one would be 7 quarters if we were to do the next harmonic, and then we would again see the pattern here developing of being 3 times the fundamental frequency, 5 times the original frequency, and the next one would be 7 times. So it would be the 7th harmonic, 7 times the original frequency, with with the length of the tube equaling 7/4 the wavelength. I don't have an example problem to go along with these open and closed tubes, but I believe there is a homework problem associated with them. So my tip or hint here would be to just basically look at the way these patterns emerge of 1 quarter, 3 quarter, 5 quarters, and so on. And that will help you hopefully recognize the pattern required to answer the homework question. So moving on from open and closed tubes, we're going to look at a phenomenon that is possible with waves called beats. Now, we had talked in the last chapter about if you've got a wave like this heading in this direction, and a wave on the same positive side of our baseline here coming in this direction, and when they come together, they are going to have what's called constructive interference. They're going to double the amplitude of this wave. Whereas if we had a wave on the positive side of this baseline and a wave on the bottom side of it, and these two waves come together, when they meet each other, they're going to have destructive interference. They're going to essentially cancel each other out, and there will be no wave here at all, not on the positive or negative side. There will just simply be no wave there. So what that does in terms of sound waves, if you have two waves coming together, at one at the positive peak of its wave and the other at the negative, you can have these instances of the two waves canceling each other out. Or if they're both cresting right at the right time and they hit each other, you can get an increased effect. So if you were to, for instance, play two sound waves that have similar tones but slightly off in their frequency, they are going to kind of come into and out of phase, silencing each other and actually increasing the amplitude. I've got a video from YouTube that I've posted or will post to Blackboard that illustrates this concept audibly. It makes more sense to actually hear what's going on. Let's look at an example problem that focuses on this idea of constructive and destructive interference of audio waves. If we have two speakers emitting a tone that are 1 meter apart, so this distance here is 1 meter. A person stands 4 meters from one speaker, so this distance right here to the first one, let's say, is 4 meters. 4.00. I should write out the significant figures, and this should be 1.00. So how far should this person stand from the second speaker? What should this distance be in order to detect destructive interference when the speakers emit a 1150 hertz sound? And we'll assume that it's at room temperature. So basically what we're saying here is you can find a spot in the room, a perfect sweet spot, where if these two, they're not producing music, just a constant tone, but you can find a spot right in the room where those two tones will cancel each other out, where the one is at the positive crest of its wave and the other's at the negative, and they cancel each other out, and so you actually hear nothing. The two sounds will cancel each other out. Well, what we need to do is we need to make sure that the distance to the second speaker is the distance from the peak to the bottom. That's half of a wavelength. Okay, so we want the distance to this speaker to be 4, and then either plus or minus half of a wavelength. And if we do that, then we'll assure ourselves that while this is at the peak of its wave, the other will be at the bottom. And as I glance down at the timer on my video, it looks like I'm coming up on less than 30 seconds to go. So I better stop right here and resume this example problem in the next video.